Hello everyone, and welcome to our next lab exercise. This is a lab about adding vectors, and what we're going to do is we're going to add vectors using the mathematical component method. We will also add them using the graphical method, and then we will compare those two methods to each other to verify that they are in agreement. We will also apply several forces to a force table at the very end to show that forces do in fact add according to the rules of vectors. Before we get into the exercises, we need to learn several things. One of the important things that we need to learn is how to take a physical quantity and represent it to scale on a piece of paper. The procedure is actually pretty simple. It's very simple to what we do when we do unit conversions and dimensional analysis. In this exercise, we are going to represent forces on a piece of paper. We are going to use the scale that 10 centimeters on the paper represents 1 Newton of force. Now, it doesn't make sense to put an equal sign in there because you can't directly compare centimeters to newtons. They're fundamentally different things. What we can do is introduce a new symbol, a double-headed arrow. The arrow means 10 centimeters represents 1 Newton, or 1 Newton is represented by 10 centimeters. However, when you do calculations, you use this just like an equal sign. For instance, one of the things we're going to have to do is convert a force in newtons to a distance in centimeters that we're going to draw on a graph. Let us suppose that the force is 1.53 newtons. When we want to find the distance that represents this, we use dimensional analysis, but we use this symbol and this conversion instead of a conventional conversion. So we write our force, and then we draw a long double arrow, just like we would the fraction sign, and we put our conversion here. And in this case, since we wish to get rid of newtons, we push that in the bottom. You always put the unit you wish to get rid of in the bottom. We put the other unit in the top. The newtons cancel, and we get 15.3 centimeters. So we can say that a force of 1.53 newtons is represented by 15.3 centimeters. And so we can write it like that. So to go from the force over to a distance, we use dimensional analysis, but with this new sign, and we use this conversion. Now, in this exercise, we are also going to have to go the other way. Suppose we measure a distance on our graph, such as perhaps the distance is 17.5 centimeters. So we wind up with a vector that is 17.5 centimeters long. And we want to know what force does that represent. we write our distance, we write our long double-headed arrow, and then we use our conversion, putting the unit we wish to get rid of in the bottom. In this case, the centimeters goes in the bottom, the 1 Newton goes in the top, and the centimeters cancel, and we get 1.75 newtons. So we can say that a 1.75 Newton force is represented by a length of 17.5 centimeters on the graph. And this is how, in this exercise, we will be converting from forces to distances on graph, and from the distance on a graph back to a force. In the exercise today, we're going to need to use a protractor. The best thing you can do is to go and buy one. Walmart will have them, the bookstore will have them, drugstores will have them. There are all kinds of places you can find them. However, if you can't find one or you don't want to bother, included in the course package is this sheet. And if you take this and carefully cut out the protractor, you will be able to use it in today's exercise. When you cut it out, it's important to cut directly across the bottom and very accurately around the top semicircle. When you cut across the bottom, you want to cut off those little feet so that your final protractor looks like this. Notice I've cut directly across the bottom on the 0 on each side, and I've cut the little feet off, if you want to call them that, on each side, and very accurately cut along this bottom line. Very important not to cut any further, and also to cut enough. You must cut exactly along that bottom line. Too much or too little, and the protractor will not be accurate. One of the things we're going to have to do today as part of the exercise is to use a protractor to measure an angle. In today's exercise, one side of the angle is always going to be aligned with the x-axis. It may not be on the x-axis, but at least it will be parallel to the x-axis. The other line could slope up, or it could also slope down. The point where the two lines of the angle meet is called the vertex of the angle. What we need to do to use a protractor to measure the angle is to take our protractor, and you can take either one that you bought or the one that you cut out of the paper. And on the protractor, there is a little arrow in the middle, and it points to the vertex point of the protractor. Some protractors, if you bought a commercial one, might have a hole there, but make sure that the hole truly is the vertex point. It should be right along the 0 line that goes across the bottom of the protractor. What you have to do is place the protractor so that the vertex of the protractor lines up with the vertex of the angle, and make sure that they coincide exactly, and then orient the protractor so that the bottom of the protractor is exactly lined up on the baseline of the angle. In this case, we line it up like so. We line it up there. And then you read where the line crosses on the semicircle. Don't use the scale where the numbers are greater than 90. All of our angles are less than 90 degrees. In this case, it's a little bit above the 25 mark, probably on the 26 mark, and so this would be a 26 degree angle. Let's try another one. Again, for today's exercise, one side of our angle is going to be lined up along the positive x-axis. The other side will be whatever. This has a vertex over here. And to read our angle, we take our protractor, we line up the vertex point of the protractor with the vertex of the angle, and we make sure that it's not tilted. We make sure that the baseline of the protractor is exactly matched up with the baseline of the angle. This is at the 0 mark here, so the vertex should be at the vertex mark of the protractor. The 0 mark of the protractor should cross the baseline just like that. And once we do that, we look where the line crosses the protractor. This one crosses right here, and that looks like it's about 64 degrees. If the line happens to be below the x-axis, as it probably is going to be today if you do everything right, then you simply turn the protractor upside down. There's our angle like that. Again, we line up the protractor vertex point with the vertex of the angle, but this is obviously not going to work, so we simply turn it upside down. And we use the baseline of the protractor. We make sure that the vertices line up. We make sure that the baseline crosses at the 0 mark, so we rotate this around so that the baseline is exactly lined up with the base of the protractor. 0 is here for this one. The vertices must line up, and then we can read, in this case, it sure looks like to me that that is a 15 degree angle. And that is how you use a protractor to read off an angle. Besides reading angles, a protractor is also used to draw angles. In addition to the protractor, you need to have a very sharp pencil or a very sharp pen. You cannot use a broad pointed pen or pencil. They need to be sharp. Today we're going to need to draw two angles, a plus 30 degree angle and a minus 40 degree angle. Let's see how we do that. Our first one will be drawn over on the left side of the page, but we'll just do it here in the middle of the board. To draw the angle, first we put a point to represent the vertex of the angle. And then, today we're always measuring our angles with respect to the plus x-axis. You'll have horizontal lines on the graph paper to help you, but I'll try to do my best here. And I'll draw a horizontal line like that. And now what I want to do is I need to draw a line 30 degrees above the plus x-axis that is the correct length as determined by the first part of the exercise, where you calculate the length, the scale length that represents the force. But to use a protractor to draw a 30-degree angle, once we've drawn the vertex and we've drawn the baseline, in this case that will be the plus x-axis, we put the protractor so that the base of the protractor is exactly lined up with the baseline and the vertex matches up perfectly. You can tell that this is the case when the two vertices match up and the baseline goes through the 0 mark on the protractor. If the protractor is rotated improperly, this 0 mark will not cross the baseline. And you also must be sure that it's not too far to the left or right so that the two vertices exactly match up. Now we want to draw a 30-degree angle, so we now take a very sharp pencil or pen and we make a tiny little dot right at the 30-degree mark on the protractor. Now that that mark is there, we can take our ruler, and the ruler goes right on our mark and right on our vertex, and then we can draw our line the correct distance so that it goes right through the point that we drew, like that, and we draw this to the correct length. The length might not be long enough to take you through the point that you made. So if this is the point that you made, you may only have to be able to draw the line the correct distance with the ruler lined up and then stop at the correct distance, and then you've drawn a vector arrow of the correct length and with the correct angle. What if we want to make an angle below the x-axis? Well, you use the same procedure. Now our baseline, when we do the exercise, may not be directly on one of the lines, one of the horizontal lines on the graph paper, but you can make sure that it is parallel to the horizontal grid lines. And we again mark our vertex right there. We then take our protractor, and if we wish to make a negative 40-degree angle, we put this upside down. We again line up the vertices here, and we make sure that the baseline is parallel to the base of the protractor, not this inside line. Make sure that the 0 line of the protractor lines up with the baseline. This line should line up with the baseline. These should line up. Then we make a tiny mark at the exactly 40-degree position. It might be hard to see that on the camera, but there it is, a nice tiny dot. Then we take our ruler, connect those two dots, and we start at this and we draw this the length indicated, and put our arrow on the end of it, and then we can label this as 40 degrees. Okay, I don't label it as negative 40 degrees, I just label it as 40 degrees because it's obvious it's below the plus x-axis. I always use positive labels on my angles because the diagram shows whether it's above or below. This method can be used to draw any sized angle using the protractor. I suggest that before you start doing the exercise, you take the protractor and a blank piece of paper and you practice drawing several different angles. One of the things that you can do to see if you did it well is after you have drawn it, you can take the protractor and measure it. We put this on here, line up the vertices, make sure the baseline, so we line up the baseline here, line up the vertices, and as long as our line lines up with the 40 mark, in this case, we have drawn the angle correctly. So to check your work after using the protractor to draw the angle, you measure the angle and make sure that it is what you want. The first part of today's exercise is to add two vectors using the component method. Now, we have done this multiple times, but in this case you're going to do it very neatly and very methodically so that you can see all of the steps in a nice, clean manner. Now, the two vectors that we are going to add are a vector that is equal to the weight of a 75-gram mass at plus 30 degrees. B is equal to the weight of a 125-gram mass at minus 40 degrees. The student lab sheet will take you step by step through all the processes you need in order to do the addition by components. The first thing you need to do is you need to sketch each vector. So you'll see here it says sketch A. Now, sketch means a rough sketch. This is what I mean by sketching A. It's at about 30 degrees, like that. And for vector B, when I say sketch B, I'm looking for something sort of like that. You do a little bit better job, but I want you to be able to draw the sketches, and there's a reason for doing that. Because you need to look at the sketch and be able to see whether the components are positive or negative. Both of the components here are positive, but one of the components here is negative. It's very important that you figure out which component is the negative component. And on these, I can label the x and y axes. The purpose of sketching the vector is so that you can tell whether the components are positive or negative. There's a method to the madness. So the first thing I ask is to sketch the vector, sketch vector A. Then I say, calculate the weight of a 75-gram mass. Now, weight is mg. But the mass must be in kilograms. So you must use dimensional analysis, please, where you remember that we must convert m to kilograms, where 1 kilogram is 1,000 grams. Do not say that 1,000 kilograms is a gram. That's absolutely wrong. you must convert the 75 grams to kilograms, and then multiply it by G. And you can do this conversion and the calculation of the weight where it says calculate the weight of the 75 gram mass, show your work in that space provided. Neatly. Neatly. And then there's a place where it says give your answer. Once you have the force in newtons, since we're going to use it in the second part of the lab, I ask you to find the length needed on a graph to represent the weight of a 75 gram mass at 30 degrees. You use the scale . 10 centimeters corresponds to 1 Newton, and find the length that you'll need for the second part of the lab when you're going to make the graph. We won't use the result of this calculation as part of the first part. When you calculate the components of A vector and B vector, they are in newtons, not in centimeters. We calculate the length needed on a graph for use in the second part of the lab. But then we go back to using the actual weight. I then ask you to calculate the x component of A and the y component of A, being very careful to get the sign right. Okay? Get the sign right. Again, both of these are plus, so there's no trouble there. But don't switch the x and y components. One goes with cosine, one goes with sine. I leave it to you to work that out. So you calculate the x and y components in newtons. Then you repeat all of that for vector B. You calculate the weight of the 125 gram mass by converting the 125 grams to kilograms. You then multiply that result by G, and you will get the weight of the 125 gram mass in newtons. I then ask you to please find, using a scale of 10 centimeters corresponds to 1 Newton, what is the length of the arrow you're going to be drawing in the second part of the lab. I showed you how to do that, so you do that and fill it in. Then you go and you calculate the x and the y components of vector B. One of them is going to be negative. Be sure you get the signs correct. If you mess up here, all of your calculations that follow will be incorrect. Once you have the x components of A in newtons and the y components and the x and y components of B in newtons, you can then go and you can calculate the component of the resultant vector r, where r is A plus B. We know that Rx is AX plus BX. Ry is AY plus BY. Show your work. Show all work. Some of these I say be sure to show your work. You show all your work, period. Okay? Then I'll say find the magnitude of R. Once you know Rx and Ry, you use the Pythagorean theorem. And I will give you this hint. One of the components of R turns out to be negative. One component is positive and one component is negative. However, when you calculate the magnitude of a vector, you never use the negative sign because it is squared and the negative sign goes away. You always use positive numbers here when you use the Pythagorean theorem. So I ask you to calculate the magnitude of R showing your work, and then I ask you to calculate the angle phi, where phi is the tangent inverse, and I use an absolute value here. This guarantees that you will get a positive angle. All right? And then, based on the sine of Rx and Ry, I ask you, is this angle above or below the plus x axis? Is it above or below the plus x axis? Explain your answer. I don't want just a yes or no. I want to say it is blah, 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 because this component is this sign and this component is that sign. I want you to justify your result. Okay? All right? And the blank for that, I think, is on the next page. I might fix that. Okay? So that is the component method. You calculate the magnitude, the size of the angle, and is it above or below the x-axis. Okay, is it above or below the x-axis? All right. And also, I believe earlier, I asked you to sketch R. I want a sketch that properly takes into account the sign, the possible sign of these, and then I want you to use the sketch and the Pythagorean theorem and trigonometry to find the angle and figure out whether it's above or below the x-axis. And that is the component method of adding vectors. The second part of our lab is to graphically add the two forces. Now, if you did the first part of the lab correctly, you should have found that the first force is 0.735 newtons, and that translates into 7.35 centimeters on our graph. Okay? You should have also calculated that force B is equal to 1.23 newtons, which translates into 12.3 centimeters, and that this is at plus 30 degrees and B is at minus 40 degrees. So this is a double check. You can double check your work. Now, what we want to do is graphically add these two vectors. Starting at the left edge of the graph paper, here's the left edge of the graph paper, and exactly in the middle of the graph paper, we make a mark on one of the grid lines, right in the middle. Make a mark on the grid line right in the middle. So we've got our x-axis is there. Now, we need to draw a line 7.35 centimeters long at an angle of plus 30 degrees. Using our protractor, like I showed you, we draw an angle of exactly 30 degrees. And I'm going to make my lines much bigger so you can see them on the screen. So I'm going to make it about 5 times bigger. And so I'm going to make this considerably larger. It won't be So we put our line here. We line up the line from our protractor. And this is only going to be approximate for me. You do a much better job. And I want this to be about 35 centimeters long. Like that. Put an arrow on the end. We label. I want yours to be just like this. And I want you also to label this. This is 7.35 centimeters corresponds to 0.735 newtons. There's our first force vector. The second one has to be 12.3 centimeters long and an angle 40 degrees down. Now this is where people get confused. When we draw the next vector, we have to move our origin from here up to here. So we move our origin up to here, and right at the end of this first vector, which probably doesn't fall on a grid line, we draw a new x-axis. It will not fall on one of the grid lines, but it must be parallel to the grid lines. This new x-axis must be parallel to the horizontal lines on the graph. So we move our origin up to the end of the first vector because we're going to put these head to tail. The rule is you put the two vectors head to tail, and then you draw a line from the tail of the first to the head of the last, and that is the resulting vector. Now we have to draw 12.3 centimeters at minus 40 degrees. We take our protractor, and since it's negative, we put it upside down. We put it upside down. We line up the vertex. The new vertex of our new angle is up here, not down here. It's up there. And so we're going to draw a line. Line up our vertices. Line up our baseline. Make a delicate spot at exactly the negative 40 degree mark, 40 degrees down. And I need to make this about 60 long because I'm making this about 5 times as big. So I put this on here, line up this here, got to turn this around. About like that. And I've got to make this like that, like that, where on your paper this is 12.3 centimeters corresponding to 1.23 newtons. And then we put that there, okay, like so. So this represents our first force, 30 degrees up, 0.735 newtons or 7.35 centimeters long. This is 40 degrees down from the plus x-axis, the new plus x-axis. We put them head to tail, and the rule for graphically adding vectors is we now draw a line from the tail of the first to the head of the last, and this represents that is the resulting sum of those two vectors. Now, if I measure the angle here, want to measure, this is the angle that I'm going to measure. This is phi. That's angle phi. That's clearly, you can see that this is going to be below the plus x-axis. We measure it with respect to the original plus x-axis. And when I measure it here, by golly, I'd say it's about 15 or 16 degrees. That's my measured angle. And in the handout, I ask you to compare that 16 degrees to the angle that you got by the component method. They won't be perfectly the same, but the question I ask is, within experimental and graphing error, is this angle the same as the one you get by calculating the components? And of course, if you do it right, it's going to be pretty close. Next, we want to figure out the magnitude of the result. Now remember, I drew these about 5 times bigger than they're supposed to be, and this is measuring about 79 or about 80. It's almost 80, and a fifth of 80 is, this is about 16 centimeters long, and that is measured. I just measured that. I don't think you'll get 16 centimeters. I think you'll get something bigger. I'm off a little bit here. I'm not being real accurate. Okay? Once I know that this is measured, back on the worksheet, I say, write down the measured value. This is on the worksheet now, not on the graph. And you can convert this back, and what I get is, let's see here, we draw this out, our double header arrow, and from this we know that 10 centimeters corresponds to 1 Newton, and so my graphical result is about 1.6 newtons. I think it's a little bit bigger than that when you calculate it using the component method. And then I ask you to calculate on the graph or on the worksheet, what is the percent difference? This is our graph. So the question is, within experimental error and drawing error, obviously, is this about the same as what you get with the component method? If you've done things accurately, it should be reasonably the same. But you can calculate the graph value minus the component value, which we'll just call R, divided by the component value times 100%, and that will tell you what is the percent difference between the two values. It's doubtful that it will be 0 because there's error in the graphing and drawing and the angles and everything else. But within reason, the angle should be about the same. Don't calculate a percent for the angle. Don't calculate a percent difference for the angle. Just, are they about the same, and make a comment. And then you can calculate a percent difference for the magnitudes. Then you can write, what did you learn in this whole exercise? You can write your summary. And what we'll do next, the very end here, is we're going to take this force and this force, and we're going to put them on a round vector table, as it's called, and then we're going to add to them the opposite of this. We're going to try and add a force that points the other way. The result of these two vectors points down about 15 or 16 degrees, and has a magnitude of about 1.6 newtons. I'm going to add another force this way on the vector table that is exactly opposite that. And if force truly adds as a vector, when you have a vector and its opposite added together, the result should be 0 and the force table should be balanced. And we'll go and take a look at that. This is the force table that we will use to validate the methods of adding vectors that we have used so far, and also to show that force is a physical quantity that adds as a vector. The table is round and is graduated in degrees around the outer edge. In the center, there is a small white ring to which we apply forces. At the moment, 3 forces are applied to the ring. The one at the bottom is actually slack and has no force on it, so ignore that particular string. The forces are applied by hanging weights. And the force of the weight is transmitted through a string over a pulley and to the ring at center. Right now we have a force at plus 30 degrees equal to the weight of a 75 gram mass. Also, we have a force at minus 40 degrees, or 320 degrees. 320 subtracted from 360 gives 40, and this is being applied from a 125 gram weight, which is hanging over the edge. Now, we calculated earlier that the sum of these two forces is equivalent to a force of 1.64 newtons applied at an angle 15 degrees below the plus x-axis. So what we have done here is applied a 1.64 Newton force at an angle of 15 degrees above the negative x-axis. And that force is coming from a set of weights hanging over the end. It should be 167 grams, but it turns out, because of experimental error, it is actually 166 grams here. When that force is applied to balance the sum of the other two, we find that the 3 forces cancel out and the ring is in equilibrium, showing that vectors do add, as we said, and that force is in fact a vector quantity. Also notice that if we disturb the ring, it returns to equilibrium, and that is because disturbing it changes the angles and they no longer add up to 0. As long as it's in the center, the magnitude of the forces are correct, the angle of the forces are correct, and they all add up to 0. Proving that vectors do add by the component method or the graphical method, and that force is indeed a vector quantity.